Good day, students. Today, let us learn about the Fraunhofer diffraction of a double slit and its intensity distribution. Now, what do you mean by a double slit? Now, this picture shows the nature of a double slit. We have two very small openings of width, that is in the micrometer scales, and these two slits can be placed at a few centimeters apart. The distance between these two slits will be in the order of centimeters. Slit width is defined as small a and the distance between the slits is defined as small b. Here, let us take into account two slits. We have two rectangular slits AB and CD. The dimension of the slit width is small a and the distance between the slits is small b. We have a screen placed in front of the slit. This line defines the optic axis. When light passes through these two slits, they diffract, and the diffraction pattern is focused onto the screen using a lens. So a convex lens focuses the diffracted beam onto the screen. Here, the point of focus is taken to be P. Now, when the beam is diffracted through the edges of the slits, they diffract at an angle of theta and they are focused to a point P dash. P dash can be a point of minima or maxima depending upon the path difference between the diffracted rays. So we will measure the path difference between the points A and C. For that, we draw a normal between these 2 points. And the angle NAC will also be equal to the diffracting angle theta. Path difference will be the distance CN. So depending upon the path difference, P dash will be a point of maxima or minima. And it is assumed to be at a distance of x from the center P. Now the diffraction pattern formed here is due to two factors. The first factor is the interference between the secondary waves from the two slits, and the second factor is the diffraction effect from each slit individually. Now when light passes through these two slits, each slit produces its own secondary waves and these waves can interfere between each other. Okay, so there will be the interference pattern between these secondary waves and the diffraction pattern due to each slit. Now let us look into the diffraction effects first. On the screen we have different regions of maxima and minima that follow the conditions of path difference. So the nth diffraction maxima will be seen at positions where path difference is equal to a sine theta dn is equal to odd integral multiple of half wavelength. Here n can have values 1, 2, 3, etc. Here the path difference is due to the rays diffracted through a single slit. Okay, so it will be only a sine theta. Here the path difference is between the rays diffracting from a single slit. Okay, and dn is suffixed to show that it is due to diffraction. We have the nth diffraction maximas following the condition of path difference is equal to a sine theta dn is equal to integral multiple of lambda, where n has values 1, 2, 3, etc. Now, let us look into the interference pattern produced between the secondary waves from two slits. The nth interference minima can be seen where conditions for path difference a plus b sine theta im is equal to odd integral multiple of half wavelength. And here m can have values 1, 2, 3, etc. Path difference is produced between the rays that are diffracted from two slits. Hence, we have the term A plus B sine theta. We can understand it from the geometry. The suffix im is used to represent interference for the mth order, and m can take any integer values. The nth interference maxima are seen where path difference obeys A plus B sine theta im is equal to integral value of lambda. Here the angular separation between any two nearby maxima or minima is calculated from the sine theta im. Okay. So sine theta im can be seen to be proportional to lambda divided by A plus B. Hence, angular separation is inversely proportional to A plus B. Now from the conditions mentioned here, let us take two into consideration. The interference minima are seen at sine theta im is equal to odd integral multiple of half wavelength divided by A plus B. And diffraction minima are seen at sine theta dn is equal to integral multiple of lambda by A. Here we understand that theta im is very much smaller than theta dn, because theta im has a factor of A plus B in the denominator, whereas theta dn has only A in the denominator. Hence, a number of interference minima lie in between two nearby diffraction minimas. Hence, this pattern is observed on the screen. Okay, so here, according to diffraction, we have the central bright region surrounded by two minima, and between these two diffraction minimas, we have a number of interference minimas and maximas. Okay. In certain cases, the interference maxima will coincide with the diffraction minima, and hence the maximas will be absent. Let us look into the conditions. We have the condition for interference maxima to be A plus B sine theta im is equal to integral multiple of lambda, and condition for diffraction minima to be A sine theta dn is equal to integral multiple of lambda. So let us look into the first case. A equals B. It implies that 2A sine theta im is equal to m lambda and A sine theta is equal to n lambda. Now comparing these two equations, we get the relation that m is equal to 2n. Okay. So here the second, fourth, sixth orders of interference maxima will coincide with the first, second, third orders of diffraction minimum. Okay, so here these maximas will be absent. Now in the next case, where 2A is equal to B, that is, the distance between the slits is twice that of the slit width. This implies that 3A sine theta im is equal to m lambda and A sine theta dn is equal to n lambda. Comparing these two equations, we arrive at the conclusion that m is equal to 3 times n. That is, the third, sixth, and ninth, etc. orders of interference maxima will coincide with the first, second, third, etc. orders of diffraction minimum. Hence, these maximas will be absent. Now, in the next case where B is equal to 0, it implies that there is no distance between the slits. The slits join, and hence all the interference maximas will disappear. Now, let us mathematically tabulate the intensity due to double slit Fraunhofer diffraction. The resultant of each wave from the slits AB and CD can be written as A is equal to A naught sine alpha by alpha. where A is the resultant amplitude. These two red vectors represent the two waves from the two slits. Let delta be the phase difference between these two waves, secondary waves, and the path difference between the secondary waves is given as delta is equal to 2 pi by lambda times A plus B sine theta. When they superimpose, they produce a resultant wave shown in the black color, and it can be written as the resultant on the screen A square is equal to amplitude square of first wave plus amplitude square of second wave plus 2 times amplitude of first wave into amplitude of second wave cos of phase difference between them. That is the relation that we have written down here. Simplifying it, we get A square is equal to 4 times A naught square sine square alpha by alpha square into cos square beta. Here we have used the trigonometric relations 1 plus cos theta is equal to 2 times cos square theta by 2, and delta by 2 is being substituted with beta. We can write the resultant intensity I as A square, that is 4I0 is equal to sine square alpha by alpha square into cos square beta, where I0 is equal to A naught square. And here the term sine square alpha by alpha square represents the diffraction pattern due to single slit, whereas cos square beta represents the interference pattern due to the two slits. Also, the intensity has increased 4 times in the double slit case. Hence, we have 4I0. So, this figure represents the single slit diffraction pattern. And when we have two slits, we have the diffraction pattern due to each slit merging with the interference pattern due to the two slits. And hence, we get the enveloped pattern seen here. The diffraction pattern consists of the interference pattern due to two slits enveloped by the diffraction pattern due to a single slit. Now let us distinguish between the single slit diffraction and double slit diffraction. In the single slit diffraction, we have a central bright maxima surrounded by secondary maxima and minima of decreasing intensities on both sides. Whereas in the double slit case, we have equally spaced interference maxima and minima within the central maxima itself. Now, for the single slit diffraction, intensity I1 is given as I0 sine square alpha by alpha square, whereas for the double slit diffraction, intensity I2 is given as 4I0 sine square alpha by alpha square cos square beta, that is equal to 4 times I1. In single slit diffraction, the maxima and minima spacing depends only on the slit width A, whereas in double slit diffraction, maxima and minima spacings depend on both slit width A and distance between slits B. The figure here represents the diffraction pattern due to one slit in red line and the diffraction pattern due to two slits in blue line. Notice the difference in the intensities. Well, that's all for today. Thank you.